with the ocean as my guide.
Good day everyone! Today we're going to show you how we computed the surface area and volume of our low-poly 3D wave model in digital. At first, it looks like a complicated 3D shape because of all the triangles, but actually, it's made up of repeating equilateral triangles, which makes the computation easier. The plan is simple. First, we understand one triangle, and then we use it to find the totals for the whole wave.
So let's start with the triangle, because this is the basic building block of the wave. The triangle are equilateral, which means all sides are equal and all angles are 60 degrees. This is important because in 3D modeling and low-poly design, equilateral triangles fit together perfectly. We also know that if triangles are equal, the math becomes simpler, and we can multiply by the total number to get surface and volume. So the triangle dimensions we assume is the side length is equal to 20 cm, and the height is calculated using the formula for an equilateral triangle.
Next, we look at the whole wave and try to figure out the overall size. The width is 160 centimeters, the height is 80 centimeters, and the maximum depth is 35 centimeters. We got this number by imagining a grid over the wave. Each triangle is like a grid cell. By counting how many triangles fit across enough, we can find the overall dimensions of the model. This is why grid-based assumptions are acceptable in design and geometric projects.
Now let's count how many triangles make up the wave. This is important because we will use this to multiply the area and volume later. The first step is to find how many triangles are there along the width. The width of the wave is 160 centimeters and the base of the triangle is 20 centimeters. We will need to divide the width with the base. 160 divided by 20 is 8, so there are 8 triangles along the width. But triangles interlock, one is pointing up and one is pointing down, so when you double it, there will be 16 triangles per row. The second step is to find the vertical count. The height of the wave is 80 centimeters and the height of the triangle is 17.32 centimeters. 80 divided by 17.32 is approximately 4.6. So we need to round it and it will be 5. With alternating orientation, up and down triangles, you will need to double it so there are 10 rows. First step is to find how many triangles are there along the base. 16 times 10 is equal to 160, so there are 160 triangles along the base. The fourth step is adjusting for the shape of the wave. The wave has extra triangles in crests and folds, so we'll add 20% more. When we counted triangles, we first got 160 from the base grid, but the wave has curves and crests, so we need a few extra triangles to fill those areas. Instead of counting each one, we added around 20% more, which brings the total to 192 triangles. This way, our computation matches the actual shape better. The computation is 160 plus 0.2 times 160 is 192, so we got 192 triangles. So the whole wave has about 192 triangles. This number will help us calculate the total area and volume. By counting this, we can justify our numbers instead of guessing.
Next, we look at the whole wave and try to figure out its overall size. The width is 160 cm, height is 80 cm, and a maximum depth of 35 cm. We got these numbers by imagining a grid over the wave. Each triangle is like a grid cell. By counting how many triangles fit across and up, we can find the overall dimensions of the model. This is why grid-based assumptions are acceptable in design and geometry projects.
So each triangle has a depth because the wave is 3D. So we treat this like a triangle prism. The formula for triangle prism is volume is equals to base area times depth. Substitute number, volume is equals to 173.2 times 5 is 866 cubic centimeter for one triangle. This means each triangle has a 3D volume of a 866 cubic centimeter, then we just multiply by total triangle for the waves.
Now, we calculate using 192 triangle. So the whole wave has a surface area of 33,254.4 centimeters squared and a volume of 166,272 cubes. This shows that by breaking it into triangles, even a complicated wave can be computed accurately. We started with one triangle to understand the basics.
We counted how many triangles fit in the wave using the grid method.
We used formulas for area and volume to find totals.
We only changed the vertex heights to make the wave shape. The triangles themselves stayed the same size.
This method makes a complicated 3D shape easy to calculate.
Hit the boulevard, hear the tires screech. Soundtrack of